Welcome to this course on renewable energy systems. In this course, we will focus on one of the most powerful engineering tools used in renewable energy design and structural integrity studies, the finite element method, or FEM. While renewable energy is often thought of in terms of wind turbines, solar panels, hydro systems, and bioenergy, all of these technologies rely on structural components, materials, and designs that must withstand stress, strain, and complex environmental forces. FEM provides us with a systematic framework to analyze these stresses and optimize the safety and efficiency of renewable energy systems. In the first module, we will introduce the basics of stress analysis through FEM, review continuum mechanics concepts, and walk through one-dimensional and two-dimensional finite element problems. We will also cover plane stress and plane strain conditions, and explore the theoretical foundations such as the energy method, variational principles, and Ritze's approach. Section 1: Introduction to Stress Analysis by FEM. Stress analysis is at the heart of engineering design. In renewable energy systems, structural elements such as turbine blades, photovoltaic module frames, and hydro turbine shafts are continuously subjected to forces. These forces create stresses and strains that, if not properly understood, can lead to premature failure. The finite element method is a numerical technique that breaks down complex structures into smaller, manageable elements. By solving the governing equations on each element and assembling them, engineers can approximate the behavior of the entire system. This approach has revolutionized engineering design because it allows us to analyze highly complex geometries and loading conditions that would be impossible with simple analytical methods. Section 2: Basic concepts and types of elements. At its core, FEM is built on a few fundamental concepts. Discretization: the structure is divided into finite elements connected at nodes. Element types: these can include one-dimensional elements like rods and beams, two-dimensional elements such as triangles and quadrilaterals for surfaces, and three-dimensional elements like tetrahedra and hexahedra for solids. Shape functions: these define how displacement within an element is interpolated from nodal values. Assembly: all elements are connected into a global system of equations representing the whole structure. Boundary conditions and loads, applied forces and constraints are introduced to make the system solvable. Different element types are selected depending on the problem. For example, a solar panel frame under distributed loads may use beam and shell elements, while a wind turbine blade might require 3D solid elements for greater accuracy. Section 3: Linear static analysis. One of the simplest applications of FEM is linear static analysis. In this case, we assume that loads are applied gradually and the material responds in a linear elastic manner. This means stresses are directly proportional to strains, and no permanent deformations occur. Linear static analysis is widely used in renewable energy systems for routine checks. For instance, engineers may use it to ensure that a wind turbine tower can support its own weight and resist static wind loads, or that a hydro turbine casing does not deform excessively under static water pressure. Section 4: Review of continuum theory. Before diving deeper into FEM, it is important to revisit continuum mechanics. Continuum theory assumes that materials are continuous, even though they are composed of atoms and molecules. The basic quantities include displacements, changes in position of points in the body; strains, measures of deformation derived from displacements; stresses, internal forces per unit area resisting deformation; constitutive relations, equations that connect stresses and strains, such as Hooke's law for linear elastic materials. This theory provides the foundation for FEM because it defines the governing equations of solid mechanics that we approximate numerically. Section 5: One-dimensional and two-dimensional FEM problems. To understand FEM, we start with one-dimensional problems, such as a bar under axial loading. These problems are straightforward and provide the foundation for understanding stiffness matrices and nodal displacements. Next, we expand to two-dimensional problems, which are especially important for analyzing thin structures like solar cells, membranes, and shells. Two-dimensional elements are used in plane stress and plane strain conditions. Plane stress applies when one dimension, usually the thickness, is very small compared to the other two. For example, the thin sheets used in solar panel assemblies can be modeled under plane stress. Plane strain applies when deformation in one direction is negligible compared to the other two. This is common in long underground tunnels for hydroelectric projects. Section 6, Energy Method, Variational Principles, and Ritz's Method. One of the powerful aspects of FEM is that it is grounded in energy principles. The total potential energy of a system includes strain energy stored in the material and work done by external forces. Energy method ensures that the approximate solution minimizes the total potential energy. Variational principles provide the mathematical foundation, ensuring equilibrium, compatibility, and boundary conditions are satisfied in an approximate sense. Ritz's method, a specific variational approach where displacement is approximated by a series of functions that satisfy boundary conditions. FEM can be seen as an extension of Ritz's method, but applied locally to each finite element. These concepts are crucial for understanding why FEM works and why the solutions are stable and convergent. In Module 1, we introduce stress analysis with FEM, covered the basic concepts and types of elements, reviewed continuum mechanics, and worked through one-dimensional and two-dimensional problems under plane stress and plane strain. We also touched on the theoretical foundation with energy methods, variational principles, and Ritz's method. This module builds the theoretical understanding necessary for practical applications in renewable energy systems.